Thank you everyone for joining us for our workshop on behavior priors in reinforcement learning for robotics. I'm Krishan, I'm one of the organizers, and yeah, we're just going to start right away. So basically, I'll give a brief introduction to what this topic is that we're gonna be discussing throughout this workshop, and then we'll go straight into the invited speaker talks. Following these invited speaker talks, we're going to invite each of the speakers to join us for a panel discussion. And following that, we'll have spotlight talks from all those authors who had accepted papers, and then we'll conclude the workshop after that. So I realized that basically we have a diverse range of researchers coming to this workshop across controls, robotics, machine learning. So I thought I might just give a quick overview on what reinforcement learning is, just to give you some context of what we're trying to do in this workshop. So basically, reinforcement learning is a trial and error based control approach where an agent directly interacts with its environment in order to learn an optimal policy. So basically, we have two entities. We have an agent which can take an action in an environment, and we have an environment which will give a new state and a reward to the agent, and then this loop continues. At the heart of reinforcement learning, we have the objective, which is to maximize the expected sum of cumulative rewards or discounted rewards. And basically, the agent collects all this experience, state, action, reward experience from the environment, and it uses this information to optimize this objective function. But one big problem with this is reinforcement learning is highly sample inefficient. So in order to learn this policy, it has to collect all this data from the environment. And one problem with this is it usually does this randomly. So it usually relies on random search of these various actions that it can take in the environment. And this can be particularly hard to learn a policy with. At the same time, these algorithms the current algorithms don't make effective use of the data that they've got to learn the policy. So overall, this makes reinforcement learning highly unsuitable for real-world robotics. And that's sort of the overall motivation for this workshop, is how can we start getting reinforcement learning to work on real-world robots by tackling the sample inefficiency problem. And one large area in current research to tackle the sample inefficiency is the deliberate use of prior knowledge within reinforcement learning, and we refer to this as inductive biases. Right? And inductive biases in reinforcement learning can take various forms. And I actually made a crude a spectrum here of the level of abstraction from the task that these biases can take. So at the most abstract level, we have like network architecture. So we don't have too much information about the task coming into this, but maybe we know that, oh, it's a vision-based task, so we can use that knowledge we can use like convolutional neural networks, or there's some temporal nature involved, so we can fall to RNNs. But basically, these forms of biases are more on the network architecture, or we could be hyperparameter tuning. So we might know what parameters might be suitable for a given task. But again, you can think of these as quite abstract, from like we're tuning these parameters, hoping that they'll make a big change in the downstream task. A little less abstract is reward shaping. So now we're getting a bit more intuition into how we can induce this prior knowledge to solve the particular task. So in reward shaping, we're creating a dense reward where the agent can get some feedback from the environment at almost every step that it takes, until eventually it's guided towards solving the task. And then at the least abstract part of this is what I like to think of is we have this form of inductive bias known as behavior priors. And this hasn't really been well formalized, like people have been working this area, and this is what we're trying to get across, is what is a behavior prior and what type of inductive bias is it? So a behavior prior is any form of prior that can give us useful and meaningful behaviors that we can use in the reinforcement learning framework. And what sources do we have of this data? So particularly for robotics, and why we thought this workshop would be really exciting for this ICRA, the ICRA conference, is that there's a lot of controllers developed by the classical control and robotics community, where we can get meaningful behaviors of state action relationships. So we have in a particular state, we have some meaningful action that we can take. And this has come from the vast amounts of prior knowledge that have been distilled into these controllers. And what we're trying to do is how can we make effective use of these to try and bias a reinforcement learning agent. Another form is demonstration data. So we could have meaningful state action trajectories that were collected from an expert maybe playing with a joystick or controlling a robot with a joystick, and we could have that stored in a data set, and we could use that maybe to learn a policy and then continue with reinforcement learning. So very closely related to to ideas such as reinforcement learning from demonstrations. Another behavior prior could be an existing learned policy. So maybe we had an RL agent already solve one task, and we want to continually evolve that or continually build up on that, that prior knowledge. Or a bit more task agnostic is the idea of maybe options and skills, where we have temporal sequences of these meaningful state action behaviors in the environment, and maybe we can use those to facilitate learning. And just to give you an idea how people have started to use these forms of inductive bias. So again, they're just meaningful sequences of state action trajectories and how they've been used within the RL framework. So this is just a handful of examples, and just bear in mind that there's a whole heap. And we have compiled a whole heap of related work in this area on the workshop site, if you guys are interested to check that out. So one idea is residual reinforcement learning, where we actually have an existing controller or a policy that can solve a task to a certain degree, but maybe, let's say, in a manipulation task, the context or friction weren't modeled, aren't easy to model with the handcrafted approach. So we can use an RL agent to learn a delta action to try and modify the behaviors given by the controller. So we have this. So rather than an RL agent learning how to solve a task from scratch, we sort of learning a smaller subproblem where it's trying to learn how to modify an existing system. So we can add up the control action coming from a controller or a policy together with a delta action coming from an RL agent, and then we can optimize that residual policy in that way. Other ideas are KL regularized RL. This is where we've got a stochastic policy or a stochastic controller where these behavior priors give out distributions over actions as the outputs. And then how we can use these within an RL learning framework is, on top of the objective to maximize rewards, we have a constraint which tries to minimize the regularization towards this stochastic prior. And the idea is to try and tell the policy, be as close as possible to these behaviors when learning, sort of biasing towards what type of behaviors we want. Other ideas are hierarchical RL. So we have a high-level agent that can choose maybe a heap of these low-level behavior priors. And then at the low level, we just execute short sequences of meaningful behaviors. And this could be skills. It could be a handful of different controllers that can, like movement primitives, or different controllers that can do different parts of a task. And we can optimize the agent in that way. Or another idea is to actually use these behavior priors directly for exploration bias. So rather than random exploration, just sampling from a Gaussian or just sampling random actions, we can actually sample from a controller, or have a controller give us some form of exploration info, some exploration bias. So hopefully this gives you an overall idea of what behavior priors are, and puts the idea into context, like in comparison to other forms of inductive bias, why behavior priors can be a very useful and very intuitive form of bias to utilize within RL. And particularly from like with ICRA, and we have a lot of people coming from robotics, and they might be thinking, when I come to RL, do I just learn something from scratch? Do I just throw away all my control? But the idea here is that there's a nice balance that we can get, and there must be some idea where we can get these controllers and maybe extract demonstrations from them and reuse that, or maybe get the controller directly within the RL framework and try to facilitate learning in that way. So with that, we have an amazing lineup of speakers who have all been working in the area of reinforcement learning and have used priors and behavior priors in some way, form, or another. And I just wanted to thank all of them for taking the time to join us for this workshop. We have Nicholas Hees from DeepMind, Joyner Prekap from McGill University, Davide Scaramuza from the University of Zurich, Avi Singh from Google Brain, Animesh Garg from the University of Toronto, and Kelsey Allen from DeepMind. Following the invited speaker talks, we're going to have a panel discussion with all of them, which will be moderated by Dushyant Rao. Dushyant, thankfully, is filling in last minute for us. We were going to have Marcus Wolfmeyer, but he couldn't make it due to personal reasons. So thank you, Dushyant, for taking the time to join us. We had about 10 papers submitted all in all, and we accepted half of them. And since we just have a handful of them, each of all these papers will be giving a spotlight presentation, and we'll have a Q&A after each presentation for anyone to ask the presenters questions. I'd like to just thank the program committee who helped us review all these papers within a short space of time. We couldn't have done that without you. And lastly, I'd like to thank the organizers, so that's FIBA, Andrew Melnick, Kate Rackley, Nico Sonderhoff, and with support from the QUT Centre for Robotics, this workshop wouldn't have been possible without your help.